If one classification tree is good, how about a whole forest of them? Welcome to this video on classification. My name is Kevin Fiesel. I'm the proprietor of Catalxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, we looked at one of the simplest classification algorithms in CART. CART, as you'll recall, is basically a decision tree with an output for each terminal node. It's easy to implement, easy to work with, and pretty useful on the whole. But it is by no means the only, or even the best, algorithm. You see, one of the problems with CART is that it's too sure of itself. If your database size is less than 50 gigs, and your memory usage is less than 32 megabytes, and your file count is more than 10, then the answer is X. I know this because I have 3 examples that point toward X. But 3 isn't a huge number to work with, and the world is always more complex than a few if-else statements. Yet, there's no room for nuance in CART. Well, this led to a bit of intuition. If we can't have much nuance within the context of a single tree, what if we had more than one? How about we have a whole series of trees that we train? Then we could have each tree vote, and we could take the majority winner as our class of choice. But if we just trained a dozen or 100 or 1,000 trees using the same input features and the same training data sets, we'd simply get dozens or hundreds or thousands of the same answer. So we do need to shake things up a bit. And we have a couple of techniques to do just that. The first technique is called bootstrap aggregation, or bagging. The idea behind bootstrap aggregation is that we want to sample a subset of data from our training dataset with replacement. Each tree will have some percentage of the total dataset, and we can repeat rows in multiple trees. This adds some variety to how we create each individual tree. The other way we create variety comes from Leo Breiman's seminal paper on random forests. We can use a subset of features. Breiman noted that, in many cases, cutting down to a single feature worked really well for datasets, indicating that more features in a tree doesn't necessarily mean better outcomes. His rule of thumb is that a given tree in this forest should consider the square root of the number of features available to it at each split. So for example, in our heart attack dataset, we have 13 features. So every time we have a split in our tree, we could randomly choose from among 3 or maybe 4 features from the total set and ask, which of these features is the most important? The concept of purposefully limiting the amount of training data and the number of features may seem counterintuitive at first. After all, more data gives us a clearer picture of the world, and our random selection could end up with us choosing 4 low importance features. But what this does is that it forces us to create a large series of trees trying to solve for small subsets of the problem. The idea here is that each tree has the opportunity to narrow down on some important piece of information that a single aggregated tree will lose because it doesn't have the necessary levels of depth, or because it's focusing in on higher value variables to the detriment of this smaller but meaningful finding. If we have a large number of smaller trees, there is a chance some of those trees find something useful, and as we summarize all of the results, we can end up with a whole greater than the sum of its parts. In other words, random forests are a lot like Voltron, scientifically speaking. With this background in mind, let's head over to the demo notebook and see what our random forest can do. Welcome to Notebook 2. In the prior notebook, we looked at CART. This time around, we are going to look at a random forest classifier. Random forest is still in scikit-learn, but it's actually in the ensemble namespace, as we're generating a whole series of trees rather than just one. The next few steps are exactly the same as in the CART example, and I'm doing this on purpose to illustrate that, in an ideal world, the algorithm shouldn't affect the way you analyze your data. perform data engineering, split your data, or even how you perform fitting and prediction. With scikit-learn, at least, there's a consistent interface we can follow and get our results. After I've performed fitting, I can generate predictions the same way as before. The end result, when I first ran this notebook, was an accuracy of 83.5%. In practice, this is usually in the 82 to 84% range, so a solid 7 to 10 point increase over CART, despite us not doing anything special. All we're doing is taking advantage of the fact that the random forest algorithm can make use of smaller bits of information that CART would otherwise ignore, leading to better results. But this isn't the only way to build a random forest. There are quite a few parameters we can send to the random forest classifier function. I've pasted the function definition in this notebook, and we can see a couple dozen parameters. Of these, there are 7 that I called out as potentially interesting. N_estimators is the number of trees we create in a forest. The search criterion can be one of Gini coefficient, entropy measure, or log loss. We can specify other parts of the tree, including the number of levels to the tree, how many samples we need for a split, the minimum number of samples we need per leaf node, the maximum number of features to consider for each split operation, and the maximum number of leaf nodes. In this next cell, I have a collection of the parameters and some values for each that may be reasonable. If you think about 6 estimator counts, 3 criteria, 6 values for max depth, 2 ways of determining the max number of features to consider per split, and 5 values for the minimum number of samples per leaf, that's a total of 1,080 possible combinations. Let's say it takes 1 second to train a random forest given one parameter set. If so, that would take approximately 20 minutes to search exhaustively through this set. 20 minutes is a bit long for me to sit here and twiddle my thumbs, so instead I'm going to use a randomized search across the parameter space. Specifically, I'll create a new random forest classifier called RF and pass it to the randomized search CV function, along with our parameters, and a value for a number of iterations of 40. That means we are going to take 40 separate bites at the apple. Now let's run the fit function. Like I mentioned, this is going to grab a random value from the list for each parameter in our dictionary. Once we have the set of parameters, we train the model and store some information about each model. I'm going to have to vamp a little bit while training is happening, but fortunately, it doesn't take a full second to train one model on my PC, even with me recording like this, but once it's done, we will be able to compare each of the results. And there are a variety of measures we can use to gauge success. However, I will stick with the defaults for this fairly simple problem. Great, fitting finished. Let's get the best set of parameters based on our search criteria. This will spit out a set of parameters, and I'm going to spend a moment filling them into the next cell. Once I've finished doing that, I can create one final random forest classifier. By the way, I don't necessarily need to do this step because we actually do have the trained model in our randomized search CV output, but it takes less than a second to fit, so let's just go ahead and do that for the sake of simplicity. Then I can perform testing using our holdout set. This gives us a new accuracy score, which may very well be higher than what we came up with earlier. Hey, it's future me here. I'm going to stop for a moment and talk about this accuracy score, considering that it's lower than our default score was. What's going on is that with randomized search, we're only scouting out a rather small percentage of the total search space. 40 out of 1,080 possible sets of parameters, or 3.7%. That means sometimes we might end up in a crummy part of town where the best accuracy that we get is still bad. That is a risk you sometimes take with randomized search, after all. One thing I do want to point out is that the max depth of these trees is 2, and for this scenario with this heart attack dataset, I typically have a lot more success with a max depth of 4 or even 5. That change alone is worth 2 to 3 percentage points of accuracy, and it is a good reminder to us that The more you know about your data and your scenario, the less likely you are to wind up with a suboptimal solution like this one. That's all I've got, so let's go back to present me. Now, I will say the highest I saw from randomized search was around 84.6% accuracy, so let's see how close we get to that. When it comes time to visualize a random forest, I do want to note that there is no neat way to do it like we can with CART. What we can do, however, is visualize individual trees with GraphViz like we did with CART. In this case, I can visualize tree 0, the first tree in the set. There's nothing special about tree 0 other than it being the first one we created. Still, as I look through it, I can see the feature ordering is very different from what we had with CART. If I switch this to tree 20 instead of tree 0, we can see that there is hardly any likeness between these trees. This is a good demonstration of how random forest works in practice. We have this wildly different set of trees, and for each new row, we run through each of them. Each tree has some part of the solution, and if we sum up their answers, we get a pretty good picture of the whole. It's the wisdom of crowds in action, but without extraordinary popular delusions and the madness of crowds. That'll do it for the random forest algorithm, at least for now. It will come back later. As we saw, we can get a nice boost in accuracy over CART when dealing with this heart attack dataset. I think the random forest algorithm is definitely one you should keep in mind when working on a classification problem. That said, it does come with one massive drawback. As your datasets get larger, random forest requires more and more memory. As a result, you're liable to run out of memory quickly as you use it. For a small dataset like this, it doesn't matter. But if you're dealing with hundreds of millions of rows in your training dataset, you will need an enormous amount of memory to manage 500 or 1,000 trees. In the next video, I'll cover a technique that came about in reaction to this memory requirement and a couple of other factors. Gradient boosted trees. We'll have links and show notes in the description below. And until we see each other in the next video, take care.